Who's my favorite student? Sadly, it's Anne. Good old Anne Serkey. Number one. So here is the key for these equations, for radiation equations, for mass equations. The mass on the left has to equal the total mass on the right. I'm starting with 216. I have to finish with 216. Nick, the fact that there's a 216 right there means this must have a mass of 0. So I already know it's either gamma or beta, because those are the two that have a mass of 0. I started with an 84 here. I have an 85 here. These two have to add to 84, so this must be a -1.
It's a beta.
Now I know it's beta, and you can either write beta, the word beta, or you can put a B, whatever, but somehow indicate that that's beta. 1 mark for the charge, so 1 mark for the particle, 1 mark for the type of decay. Number 2, this is definitely gamma. You can put a G there for gamma, or you can put the symbol. And I know that because that's a gamma particle. And gamma has a mass of 0, a charge of 0. I started with 58. This is going to be 58. I started with 26. This is still going to be 26, which tells me this is element number 26. It's iron. For a gamma decay, the particle, the element doesn't change elements, it loses energy. And that's what this little asterisk there is. That's saying this is a radioactive iron that needs to bleed off some energy to become stable. Number 3, definitely beta decay. 1 mark for that. The total mass, 208 plus 0, 208. 81 plus -1, 80. So this must have been element number 80, which is, I have no idea. Mercury?
Mercury.
So we would read this as mercury 208 decayed into whatever TL is. I think TL is tellurium 208 by giving off a beta particle. Number 4 is definitely alpha. I started with a mass of 234, so this must be 230 because plus 4. I started with a 90. I've used up 2. This has got to be an 88. So that I still add to 90. And then it's element number 88, which is radium. 1 mark for that. 1 mark for that. One mark for this, 1 mark for this. Each question's worth 2 marks. Beta decay. 32 and I guess 16. So that 16 plus -1 gives me 15. So this is going to be element number 16, which is, I have no idea, sulfur. Definitely gamma. So it's going to be same mass, same protons. It's going to be magnesium. If I'm going to be really fussy, you should have put a star there, but I'm not going to be too fussy if you didn't put a star there. But if you did, good. That's the way of saying this is a radioactive element that needs to get rid of some energy. It's going to give off a gamma particle. If you didn't put the star there, though, I won't take a mark off. Number 7, alpha. Starting with 214, so I got to finish with 214. That must mean this is a 210. 210 plus 4 is 214. And started with 83. I've used up 2 protons with the alpha particle. This must be 81, which is thallium. Thallium. Number 8, uranium-235. Oh, they told me it's alpha, so I know this second one must be that. And so I must have a mass of 231. I must have a charge of 90. So 90 plus 2 gives me 92. So it's element number 90, which is thorium. I'm thorium about that. Nothing. Okay.
I would have laughed if I wasn't focused on writing.
But it would have been a pity laugh, but I'll take a pity laugh. Number 9, definitely beta.
And number 10 is alpha.
201, I agree. The betas are tricky. So I got started with 80. I have to finish with a total of 80. So it must be 81 here, because 81 plus -1 is 80. And element number 81 is... Oh, it's also thallium again. Number 10. What did you say it was, Raphael?
Alpha.
Yep. And we must have started with a mass of 144. We have 60 protons on the right, so 60 on the left. So it's element number 60, which is neodymium, used in rare earth magnets and in your phones. So this page is out of technically 20, I think. 2 marks each, 10 questions. If you've wrapped your brain around this, I can't call this easy marks. I'm not going to call this fill in the blank marks, but hopefully this is very doable with a calculator marks. Turn the page. We caught that there was a typo, that 9A, that should be a 92. So Kaylin, this is how we do these ones. It's going to be really, really similar. I'll answer the fusion fission afterwards so I can zoom in a little bit. Kaylin, I have a mass of 236 on the left, 1 plus 235. How much mass do I need to finish with? 236. On my calculator, and now I do need a calculator, I would type in 236 minus, I've used up 77. See it there? So minus 77 minus, and I've used up 3 neutrons. So 3 times 1, 3 neutrons, minus 3. Kaylin, how much mass do I have left? Can you read that number from the back or not? That's what goes up here. I'm going to do the same thing for the bottom. On the bottom, I have 0 plus 92. So I'll go 92 minus, I've used up 34. And then technically I should go minus 0, but will minusing 0 make a difference at all? So I'll skip that. What number's left over? What number is going to go right there? Same answer. And that tells me what element this is. This is element number 58, which is cerium, Ce. Yep.
It is fission and not fusion.
How do you know? Fission, and I put this on your green sheet, is splitting a big atom up into 2 smaller ones. So you can circle fission. 1 mark for that. I told you A was fusion. If I said that, then I was either reading upside down or I got them mixed up, and I apologize. They are easy to mix up. I always got to be careful. So, Kaylin, same idea. 1 plus 235, we're starting with 236. We'll often start with 236 because I'm trying to make realistic reactions. Here we've used up 93, so on my calculator, 236 minus 93, and then minus 3 neutrons. Leaves me with a mass of 140. For charges, I started with 92. I've used up 40. Leaving me 52, and that's going to be element number 52, which is tellurium, Te. Fusion or fission? This is again fission, breaking apart. Did I tell you that one right at least, I hope? Or
No, don't
You literally told me the opposite. You were reading it upside down. You just made me go through this solid.
So fix it and get your corrections and you'll be okay. So don't not get it wrong.
Number 3 is fission.
Number 3, fission?
Yes.
I agree. Did you get the numbers that go there, Raph?
2 over 0.
Let's see. I start with 236 again. I've used up 143 and I've used up 90. I have 3 neutrons left over. Not always going to be 3 neutrons, might be 2 neutrons, can be 4, but the most common is 3. Raph, what's this last one? Fusion or fission? D.
I didn't do that question.
Okay. This is smaller elements, and by smaller, it's going to be either hydrogen, helium, or lithium. Hint, hint. That's going to be a fusion reaction, because those are the ones that we can fuse into bigger elements. So this is fusion. Same idea, though. I ended with a mass of 4, so I have to start with a mass of 4. This must be a 2. I ended with 1, 2 on the bottom, so I have to have a total of 2 on the bottom, and this must be hydrogen. Then we need, where are we, these, Mr. Dewick? No, wrong one. Science 10. Chemistry, radiation. Come on, computer. I need the graphs. Half-life graphs. So we're dealing with carbon-14. We have 55%. So I'll find the graph for carbon-14. 55% would be halfway between 50 and 60 right there. Read across, drop down. 5,000 years, yes?
5,000 years.
1 mark for that.
130.
Number 11, some volcanic rock is being studied. By the way, I didn't mention this in the notes, but potassium-40, that's formed in lava. But while the lava is liquid, it bubbles out because it's a gas. But once it solidifies, what potassium-40 can tell us is when the rock solidified. So that's why I wrote how long ago were the rocks solidified. So potassium-40, Kaylin, that's this graph. What percent? I've on the other page. 90. So 90%, halfway between 80 and 100, right there. Drop down. What is that? Yes, nice. 0.2. 0.2 billion, which is 200 million. I'm impressed you did the conversion. Nice. So I'll write 0.2 bill, but if you wrote 200 mil, that's the same answer. If you have anything close to that, what I would really be looking for is, I think, bigger than 0.1, less than 0.5-ish. I'd take that. I would argue, though, I think it's a little further than that, but we're roughing graphs. Back page. I did the parents and the daughters first. Right from the green sheet, I said, that's carbon-14. Each one of these squares is going to be a half mark. Oh, last page out of? That's a good question. 2, 4, 6, 8. So this little question here is out of 8. And then 1 and 1. So the whole page is out of 10. Dos. On the next page, 8 marks. There's 16 squares. So 0.5 for each square. Carbon-14. Which one has a half-life of 710 million years?
Uranium-235.
So U-235, and that goes with lead-20 something.
207.
207. Argon-40 goes with potassium-40, and 235, we did twice, goes with lead-207. What is the half-life of carbon-14? 5,000 something.
Nitrogen-
Don't need to memorize that. It's on your sheet. What's the half-life of potassium-40? 1.5? I think it's 1.3. I didn't think it was a nice number like 1.5. That'd be too convenient. The universe usually doesn't give us nice numbers. And uranium-235, we already said was 710 million. Okay. I'm going to do these next 2 squares simultaneously. If I have 80% of the parent, that means there's 20% that's decayed into the daughter, because these 2 have to add to 100. If I have 60% of the parent, 40% of the daughter. If I have 95% of the daughter, Kaylin, phone away, 5% of the parent. We're almost done. This last one we'll save for last. Now let's do the age. So 80% of carbon-14, go to the carbon-14 graph, 80%, read across, and then slide down. Oh yeah, this goes up by ones. Looking at the scale, 2,000 years. And in real life, probably plus or minus a couple of hundred, because how accurate can we be? But certainly right around 2,000 years old. I agree. Uranium-235, 60%. Uranium-235, 60 drop down. Sorry? 0.5 billion or 500 million, I think is right.
Does that say under
No,
1.3
in the hallway
bill?
we're allowed to. Sorry, what?
Does that say under
0.5 bill.
1.3 bill?
0.5 billion.
No, I said,
Oh, here, 1.3 billion and then 710 million.
okay.
Potassium, 45%. Where's potassium? There it is. 5%. I guess halfway between 10 and 20, sorry, between 0 and 20, 10 would be right there. So I think 5 is right there.
I said 5.3.
I said 5.4.
Here's what I would take.
5.32.
I would take definitely something less than 5.5 and something more than about 5.1. If you want me to be fussy, I think it's close to 5.4, but I'll take 5.3, I'll take 5.2. I would not take 5 and I would not take 5.5 because it's definitely between those. So I'm going to write 5.4, and that was Bill. This last one, now I'm reading from the x-axis. So it's uranium-235, that's this graph here, and they told me it's 3 billion years old. So now I'm going to read here. Here's 3 billion. Read up and then read across. 5%. What percent must be the daughter then? 95. So do your corrections. So this page here is out of 8, each square is 0.5. And so that makes the total quiz out of 38. If you're done and you like your score and you're not going to do corrections, making sure your name is on it, put a score right there and you can hand it in. If you want to do your corrections first so that you can change your score to a perfect score, that's your homework for the next few minutes as well. But otherwise, my angels, for today, we're basically done. In about 10 minutes, I got a couple of more cool space videos to show you because I'm a nerd about those things.